Hi, as the title of this video says, here is science behind the spokes and the bicycle wheel. Thank you very much for watching. Don't forget to subscribe, like. You expected something else. Okay, fair enough. In this video I will explain why bicycle wheels are built the way they are built, why we use spokes in the first place and not some other method, and why some lacing patterns are better than some other, as well as why some wheel designs are better than some others. Also, I will address the topic whether using disc brakes puts more load on the spokes and the rim compared to using rim brakes. The video will not be very short, but I find this whole structure of the bicycle wheel quite fascinating from the engineering point of view, and the way they are built to be very strong, very durable, and yet relatively light in spite of all that. So I will try to explain how that is achieved so that you can understand why wheels are laced the way they are and built the way they are. Let us begin. In order to explain things, I like using analogies. For me it's the easiest way to understand, and that is what I will be using in this video. Now this is an important concept to understand in order to understand the analogies used in this video, what I will show right now. Say we want to hold this hub firmly in place. We could use a vise, for example, and place it in a vise, tighten it using this simple mechanism, and now the hub is held on securely. At the same time, if we wanted to hold this vise in place for whatever reason, and we had this hub attached to something or welded onto something or something similar, we could use the same principle, and if I'm holding the hub firmly secured, I could say that the vise is secured against the hub and it's held firmly in place. Similarly, when we have our bicycle wheel, our main goal is to have the rim held securely and firmly in place so that it doesn't wobble or bounce up or down or similar, but goes straight and turns nicely and roundly as we ride, while our hub is held in place on the frame. The spinning is done using the bearings, of course, but what about holding the rim and preventing it from moving sideways or up and down as we put some weight on it and similar? Well, to understand that, I will use a bit of opposite logic and see how we can secure the hub within the rim, because at the same time, as I've tried to explain, it makes sure that when the hub is the thing that is held on too firmly, then it also makes sure that the rim is secured to the hub. I hope this is clear to understand, and now I will get on with explaining the bicycle wheel design. To make things simpler, in this first go I will first use a cube. Let's say we have a cube. A cube is three-dimensional, but here I will just draw a cross section of the cube. And let's say I want it suspended in midair for whatever reason. Of course, I could use some sort of post to hold it in place on the ground, but in order to hold it, whatever its weight is, this post would have to be either a bit wider and a bit heavier than necessary for holding it in place, because it needs to be rigid so it doesn't fall to any side, and it needs to hold the weight of the cube. But if we happen to be indoors and have a garage like this one, then we could use a much simpler method. Let's delete this. If we are inside the garage, I will also draw it like a two-dimensional cross section, and let's imagine it is also a cube and not some other more complicated shape. We could use a very light, simple method to hold this in midair by using a very relatively small, thin string If we hang it on a string, that string will be able to hold its weight while being a lot lighter than a comparable rod or post that should hold the same weight. No matter how light the cube is, a string will always be lighter than a post. However, strings have a certain problem. For bicycle wheels, for all practical reasons regarding this topic, we can imagine them to be strings. In fact, you can build a bicycle wheel using strings. Even some spare fix-it-quickly models are sold made of carbon fiber, so that you are practically using a string. However, when building a wheel, in order to tension the spoke, which is very important, as I will explain later, we still need to use practically stainless steel rods, which a spoke is, but for all effective reasons it acts like a string, because it is not very good at taking torque, like twisting, and it's not very good at taking compressive loads. It will relatively easily bend, but it's very good at taking tension. So compression or any sort of torque twist is not something that spokes hold up very well, but tension, you can put a lot of tension. I've made a video trying to measure how much tension a spoke can take, and it's a lot more than it usually can take when it's placed in a wheel, because the rim and the hub are the weak points and they will break before the spokes break if you tension all the spokes to huge tension. So that's an important thing to note. It's very strong compared to its weight, but it's not able to take any compressive or twisting force, only tension. Okay, so to hold our cube in midair, we can use a relatively small spoke or some sort of rope or steel wire or cable. But if we wanted to prevent it from rocking side to side when we push it, or from moving up and down, we might think, okay, it's a good idea to have another cable in the bottom and to tighten each cable, because without the cable in the bottom, if we try to tighten the top cable, the cube will be pulled upwards. But if we place another cable at the bottom and tighten them both, they will be exerting a forces in opposite directions, and they will be holding our cube in place. However, if we push it on the side, this will prevent it from rocking up or down, but if we push it on the side, it will move, at least to some degree. In order to prevent that, of course, we could use the same method and put two more cables and tighten them. Now, if I were really going to try to move it, I might be able to move it in this direction. If I push it from this end or from this end a bit, and in order to prevent that and to make it really be secured, at least in the two-dimensional force directions, we might add a few more pairs of wires, cables, and now we have it more or less held on pretty tightly. Now, what about pushing towards the wall or towards the camera? Well, this construction would not be very good for that. What we could do, since it is a three-dimensional object, I'm just drawing a cross-section, would be to use some cables and attach them to a wall that is towards you or and away from you, and provide that sort of tension and leverage. And that would make a very stable cube in midair, but it would make it completely useless. Why? Because on a bicycle wheel, we do not have a cube. We have this like a, what I'm not sure what the name of this shape is, but it's like an elongated ball, like a sort of a, but that's it. We have that, and we have a rim that is necessary anyway, so it's not any extra weight needless, because we need something to mount the tire on and something to roll over or to roll onto as we are riding. So we have the rim whether we want it or not, and it's a great idea to use it to provide us with some structural strength and holding this all in place. And so the rim is relatively narrow, because if we made it too wide, it would be just needless extra weight. So it is narrow, so we might consider it to be like a two-dimensional thing just going around. So we cannot make any spokes go to the sides to prevent the hub from being moved left or right relative to the plane of the rim. It is held on to move from top to bottom or anything, but it can still move left or right. To make it stay in place, and when it's held on to in a bicycle's dropouts, to prevent the rim from rocking left or right as we pedal or ride or whatever, we use the two dimensions of the hub, the flanges that are a bit aside, and so we make some spokes go from one side, some from the other, and that creates a structure that holds it and prevents it from being moved easily left and right, or from being twisted for that matter, and prevents the rim from rocking left and right to a very high degree of stiffness. And that is done by placing spokes at an angle. Let's try to draw that. Here we have our flanges, and this is the rear hub where the cassette goes, and this is the left side of the hub. So if we have a rim like a cross section, it looks like a box. And when you cut it out like this, we have some spokes going from this angle and some spokes going from this angle, and that prevents the hub from being twisted or turned. It is not as strong as if we used to mount, to also fix it someplace like this to the sides, but it is good enough. Why? Because most loads on a bicycle happen within the plane of the rim. As we are riding straight, we are putting our weight onto the hub, and the ground is pressing onto the rim from the bottom, so that it is in line. When we are turning, I have an article explaining bicycle steering and counter steering. I'll make it pop up someplace now, but without taking too much time, you can look it up if you're interested. That's also a fascinating story about physics and how bicycles and two-wheeled vehicles, motorcycles as well, are steered. And it is very counterintuitive, just like a bicycle wheel design. So it takes a bit of thinking. You might want to read it and then let it sit for a day and read it again. And the same goes for this video. Anyway, when we are turning, basically we lean the bicycle and lean along with it. And so all the force of us that is put onto the wheel still stays within the plane of the rim. So any loads that are pushing on the rim sideways are relatively small compared to the force that pushes within the plane of the rim. So we are able to get away with this like a triangular structure to hold it in place. If that were not the case, if some huge loads were put to the side, then we wouldn't have been able to get away with this. We would have had to have a rim that is very wide and have even wider hub to have that structure a lot stronger. So that is how we achieve that stability. And if you look at this design, this is what radially laced wheels look like. And now I will try to make a picture of a radially laced wheel pop up someplace here, so we can look at it. And there is a problem with it. What is the problem? There are two problems, in fact. First problem is that all these forces are trying to rip our cube apart. The same thing happens with radially laced wheels, so flanges may crack because all the spokes are trying to pull the wheel apart. That is one of the reasons why radially laced wheels are not a horribly bad idea. They still are, but not a horribly bad idea on front wheels that use rim brakes. For everything else, they are even worse. It's a bad idea for that, but for everything else, it's next to useless, as I will try to explain. So that is one problem. The other problem happens when we try to place a sprocket onto our cube. Let's try to place a sprocket here. Okay, this is not a very good drawing, sorry, but imagine this being a sprocket, and we put some chain on it and try to put some torque to pedal and rotate our cube. Of course, this is a cube in a garage, so it should not be pedaled, turned, but when we have a wheel, we use a sprocket to propel our wheel and to turn the rim by making the rim held on firmly relative to the hub. As we are trying and managing to turn the hub, we are also turning the wheel and pedaling forward. But what happens with the lacing pattern like this, radial lacing pattern, when we are trying to apply some pedaling torque? Our cube will twist a bit depending on how tight these wires are. It will twist a bit less or a bit more, but it will twist. And as it twists, it does the following thing. It will rotate a bit, and the wires will also be moved a bit further, and this is effectively longer than this distance as it moves. It's like a triangle. Try to exaggerate it here. Let's use this section. If we have our mounting point of the wire, and we move the mounting point a bit, then we have the wire going this way, and this is longer distance than this. It's like a triangle or basic trigonometry, and that is also used for calculating the optimal spoke lengths when they are laced at an angle. And so I won't be going into that right now, but that is the basic principle. So I hope it is, if it is clear and intuitive enough from the drawing. We have, if we draw this line to be like parallel and have a 90-degree angle here, we can calculate the distance of this, because let's call it x, let's call this y, and let's call this moving distance z. But I drew it here relative from the starting point to be at a 90-degree angle, so x squared equals z squared plus y squared. Sorry for my awful handwriting, but this is larger than this, so this is longer than this. That's the mathematical proof, but I hope it's intuitive enough without that. Mathematics often gets things complicated. I prefer having them shown and visualized. Anyway, that will happen. Our wires or spokes will get effectively elongated, creating even more tightening force, even more tension, and past a certain point, depending on how strong we pedal, we will no longer be able to elongate them any further, and if this were a rim, it would start moving and spinning. But we always have that sort of micro twist at the elbow where the spokes are laced, mounted, if we use the radial lacing method. So whenever we try to pedal, we have spokes doing a bit of this and then moving the rim afterwards. So that creates a lot of force trying to rip the hub flanges apart, and it also makes the spokes twist and turn, and they are more likely to break at the elbow. We can solve both these problems using a very simple method, which is called crossed lacing. You've probably heard wheels being laced 1 across, 2 across, and similar, and here I'll explain why that is a very good idea. Let's remove all this. And let's try something else. And now something completely different, as the Monty Pythons say. Okay. Let's try doing this. I will place one of our wires to be at an angle as close as to completely parallel to our cube. I cannot make it go completely parallel when I'm using it on a bicycle's hub for practical reasons. Let's show it, let's visualize it, it's better. So, if I am making a spoke go at a higher and higher angle, past a certain point it will block the adjacent spoke hole, so we will not be able to lace the wheel completely properly, and it will also have a sort of a kink introduced by the head of the adjacent spoke. So for those reasons we cannot go at a 90-degree angle from this point to make it completely tangent, if that's the proper English term, but we can make it as close to that as possible, and that is what we try to achieve when we create a certain level of number of crosses when lacing wheels. So we've made this one wire like that, and we'll make another wire go like this, and we'll go and do that for every side of the cube. Does this remind you of our crossed lacing pattern? What we have achieved here, because all these wires are being put at a certain tension, so each of them is pulling against each other, and these two forces, if we take these two wires for example, they are trying to compress our hub. Yes, if we calculate the resulting force, it's a bit above this line, but they are more they are more angled towards, directed towards pushing the sides of the flange of the cube closer to each other, trying to compress it, instead, as we did when we laced them the other way around, instead of trying to rip it apart. The similar thing happens when we have two spokes. If one is placed like this and the other is placed in the opposite, if one is placed like this and the other is placed in the opposite direction, they will be trying to compress the adjacent hub holes, spoke holes. Instead, when we lace it radially, trying to pull them all apart. And metal, aluminum and steel hub flanges are a lot better at resisting being compressed. You cannot compress those materials very easily, not nearly as easily as you can pull them apart if you apply that sort of force. So this design is better for being able to have lighter, smaller hub flanges, and all else being equal, if you don't make them too light, it will create for a stronger structure, being able to take more spoke tension, more total spoke tension, which is important for wheel strength, as I will explain a bit later. Now, what happens when we apply the pedaling torque now? Well, here as you can see, as we are trying to pedal, to turn our spoke that is attached to turn our sprocket that is attached to our cube, we are trying to move it, this wire will get more tension. Also, this wire will get more tension as we are turning it around, and so will this one, also as we are turning it around, and this one on the bottom. These spokes are on a bicycle wheel called the trailing spokes. That is just an agreed upon nomination, and you have trailing spokes, and the ones that are sort of being pushed, that lose tension, are called the leading spokes. So here, as we are turning in this direction, this one is losing tension, and also, this one is losing tension. I will draw it. I will use a different color to draw the spokes that are the gaining tension. So we have this one, we have this one, we have this one, and we have this one. Those that are marked with red are the ones that are called trailing spokes, and the ones that gain tension as we are pedaling. If we mounted the disc brake here, they would be losing tension, and our leading spokes, the ones that lose tension when we are pedaling, would be gaining tension in that case, because the opposite force is when we are braking compared to when we are pedaling. But the principle is the same, and those spokes are marked relative to the bicycle's direction of travel. So if we have a rear hub, this is the right side, the left side, we go forward like this, and so all the spokes pointing towards the back, towards the rear, are called the trailing spokes, and all the spokes going into the direction of the travel are called leading spokes, and that is the main difference. And they behave differently when we are pedaling or when we are braking using disc brakes. For rim brakes it's a bit different, I will explain that later. So we have those sets, and we have similar pattern on the other flange, on the other side, which allows us to get the thing to be rigid, for the rim to be kept in stably in when we apply some lateral loads, not just directly into the plane of the rim. I apologize for my Tarzan English. Doing the best I can. So this is the reason why we lace wheels across, and why radial racing is not a very good idea, and why we use spokes in the first place, because they allow the greatest amount of strength using the minimal amount of weight and material, compared to using some rods. Old wheels on, if you watch some Middle Ages film, when they have those carts with wooden wheels, and those wooden wheels have very thick spokes made out of wood, and those wheels are not pre-tensioned, those spokes are not pre-tensioned, but they in fact take the load by resisting compression, because those are hard, relatively big and heavy wooden planks placed around the whole wheel. But it is a lot lighter, the whole setup, the whole structure is a lot lighter, while still being able to take the same amount of load. If you use a pre-tensioned structure, this bicycle wheel is in fact a pre-tensioned structure, and it works a bit counterintuitively compared to the old style wooden cart wheels. So, and this is generally how it works. Now I will show how it takes a load of our weight when we sit on a bicycle, and then I will go on to explain why bicycle disc brakes are not as hard on the spokes as rim brakes are, which is also counterintuitive. I hear that a lot, so that's why I wanted to discuss it. Okay, so here we have our bicycle wheel, our hub, and the ground. And the bicycle wheel is placed on a bicycle, the hub is being held onto. Here we'll take this to be a front wheel, and this is our bicycle fork, and the hub is mounted on the fork. So when we sit on the bicycle, we exert a certain amount of force downwards, and all that weight, all that pressure, the same amount of weight that we exert downwards is exerted back onto the rim by the ground. Those forces are always equal. The same amount of force that I exert when trying to push this wall is also exerted by the wall trying to push me back. So I can feel it on my palm when I press. That is that force. It's always equal, the action and reaction force, if that's the proper English term. And if that were not the case, I would be able to move the wall. Then all my force, I would use it to create some momentum, some kinetic energy by speeding up the wall and making it move. But if that doesn't happen, as it doesn't happen with the ground, then I get the same amount of force back to my palm, as is the case here. We get the same amount of force back to our rim. What happens with the rim when the force is applied? Well, it is not perfectly rigid, no matter how stiff manufacturers say it is. It never is perfectly rigid, and so in practice it will deform a bit at the point of contact of the ground. We have a tire also mounted, which also has a lot of forces, and the sidewalls also play a part. But to make this video be Less complicated, less long. I will now pretend that we are rolling without a tire. Principle is the same, the results are the same. So what will happen is that our rim will get a bit deformed. It will get bent a bit at the point of contact. So instead of being perfectly round, it will be a bit indented at the point of contact, and the outer edges near the point of contact will be a bit more widened. Why? Because it is very difficult to make a rim's circumference become, total circumference become larger than it is, because it's very stiff and because all the spokes are pulling against it, trying to compress it. So it will not be able to, as we press this in, that will create a change in circumference that will have to be compensated someplace. So those are micro movements, micro changes, smaller than a sheet of paper thickness, but they happen. So the end result is that the spokes that are at the contact area, I will draw a radially laced wheel to explain this, to have it easier to understand. For a wheel that is laced across, we would have a spoke coming from a side to this point, but the principle is the same. The spokes that are near the contact area will lose a bit of tension, and the spokes that are near the contact area to the sides will gain just a little bit of tension, not nearly as much as the bottom spoke or two spokes from two sides coming will lose. This is what it looks like. If this is the contact point, these two spokes would lose some tension, and this, the closest one to it, would gain just a little bit of tension. But the main principle is that the spoke that is near the contact area will lose as much tension as the weight put on the wheel is. So while this spoke is trying to, while this spoke is trying to pull the rim towards the hub, it will lose a bit of total tension, so the force will not be this big but smaller. The spoke will not go completely slack. If a wheel is properly built, spokes are not able to take any compressive loads effectively, and they will start bending. So when your wheel is not at a high enough tension for all the forces that it faces, when you're riding, pedaling, cornering, jumping, hitting bumps, potholes, whatever, then if you come in a situation that one or a few spokes completely lose tension, zero, and start compressing, then your whole wheel will buckle. You will have a tackled wheel, and I will try to place a picture of a tackled wheel now here to explain what I mean, and it happens in an instant. As soon as, and the reason why that happens is when some spokes lose tension and the whole structure crumbles. Explaining exactly how that happens would take a very long video, but that is the main principle. So let's move on now. That is the situation when we are handling weight. So all the loads generally, even the pedaling torque and the braking torque from disc brakes, are taken by spokes losing tension, some spokes gaining tension, but generally most of the loads, the highest loads that our bicycles faced are weight, and especially if we jump and hit something, and those are taken by spokes losing tension and the total tension of all the spokes in the wheel becoming smaller. The tension does not increase. The total tension of the wheel as you're riding, even if you are pedaling and braking, does not increase. I'm mentioning this because I've read it even on a website of one of the renowned bicycle spoke manufacturers, where they explain that their spokes are capable of taking any extra tension that happens as you ride, and I commented there and explained why spokes don't take that much extra tension, a few percent when you're pedaling or braking hard, but from weight and bumps, the wheel does not act by having the total tension increased or having any spokes increase in tension, at least not significantly. Maybe some at a certain angle, but generally speaking, no. and they couldn't really explain that, and now the article is gone from their website. I am nobody, so I don't think they were really stressed by my comment, but I hope that some engineer looked at what they wrote and said, okay, this makes no sense. I also made an experiment video where I showed that spokes can take a lot higher tension than the rim can take when you're building a wheel. So rim is the weak point and the contact of the spoke to the rim. So if you go even 150 kilo force tension on the spokes, they can take double that roughly if they are of any remotely good quality, and rim cannot take nearly as much, so it would buckle completely and be crushed and bent and whatever. So the thing is that spokes generally do not have their tension increased when you're riding and when you're putting the most stress. They do get a bit of tension increased when you are braking or pedaling, but that is another matter. And as I've explained in the section when I talked about the trailing and leading spokes, when you're pedaling, the trailing spokes gain tension and the leading spokes lose tension, and when you're using your disc brake to brake and stop your bicycle, then the trailing spokes are the ones that are losing tension and the leading spokes are the ones that are gaining tension. So it's the opposite way of trying to turn the wheel, the rim relative to the hub, but the principle is the same. Now I will talk a bit about the loads taken by the spokes when we are braking. This remains the same when we are braking. We still have weight on the bicycle, but I will remove this from the picture to have it more simply, because now I want to concentrate on the loads taken by the spokes. And to make things a bit simpler for the rim brakes and disc brakes, I will make it like a radially laced wheel. So let's start with rim brakes. We have a rim brake. It's mounted usually where the fork is, but I will put it on the top. Here is our rim brake, because to make it a bit more easy to understand and intuitive, it's very small difference. So we have our rim brake and we have the ground contact patch, and this is the direction in which we are moving. And so the momentum of our weight and the bicycle weight and I think that inertia is the name of the term. So the inertia is trying to keep the bicycle going on, moving forward, and we're trying to stop. And we apply the brakes, and rim brakes hold on to the rim at the top, trying to stop it from turning. At the same time, so they are, as the wheel is turning, let's draw the direction. As the wheel is turning in this direction, we are trying to stop it from turning. So the rim brakes will apply a force in the opposite direction. The harder we brake, the larger the force, the longer this arrow. And because the wheel is moving on the ground, we have a ground, and our body weight and inertia is trying to push it forward. As we try to slow down, the ground effectively also creates a force equal to our braking force in the opposite direction of the direction that we are moving in. So both the brake and the ground are trying to stop the wheel. And if we press the brake too hard, we might have the wheel skid against the ground and leave a tire mark, which can be pretty cool. Anyway, so effectively this part where the hub is mounted is being pushed forward by the weight of our entire body and bicycle, and our brake and the ground are trying to hold the rim in place and stop it from moving. So it is as if we are moving the rim, as if the hub is stationary, and we are moving the rim backwards, the entire rim backwards, by holding it to the top and the bottom. This is fixed and it's trying to push forward, and we are moving backwards. And what happens then is that the spokes that are towards the rear third of the wheel, roughly this section, will lose some tension, because we are moving the rim in their direction. They will gain some tension because we are moving the rim in that direction away from the hub. So these will gain more tension. They will be even more strongly pulling the rim towards the hub, they will gain, their tension will increase as we are trying to pull the rim away. While the roughly third of the spokes that are on this side of the wheel, the front side of the wheel relative to our direction of travel, they will lose tension because the rim is being pushed to that side. And if we manage to brake so hard with good enough grip, or if we make a wheel with a very low total spoke tension, these spokes might completely lose their tension, have it go to zero, and then the whole wheel will buckle and get tachoed. The same thing can happen if we tension the wheel too much, so that the gain of tension at this side exceeds the amount of structural rigidity that the rim can take. So it could start tachoing from this side. It's enough to just go twist to one side at one place, and then it's like a big wave around the whole rim and the spokes, and in an instant the wheel gets tachoed. So having the spoke tension above the, say, 80% of the total tension that the rim can take, when you add tension of every spoke on the rim and that total, if you exceed 80% of that total, or if you go with very low spoke tension, either extreme is bad and creates for a wheel that is not very long lasting, not very durable. Also, when you have spokes that are under tensioned, they will more easily break from fatigue. But that is a separate topic. I will not be going and discussing that. Here we're talking just about the wheel strength. I'll make a separate video, more than 10 people watch this. Anyway, that's what happens with the rim brakes. So the spokes that are, what about the spokes that are on the top section and on the bottom section, in the bottom section? Well, they are practically not doing anything apart from this one taking the load of our weight as we are braking, perhaps with some extra weight on the front wheel as the weight gets transferred from the rear to the front wheel, but there is nothing really worth mentioning in this context related to the top and bottom spokes. So the entire force of the braking is taken by roughly half the spokes of the wheel, maybe a bit more than half, but definitely not all of them, which means that one particular spoke at any given time, whichever ends up at the rear, is taking a lot more load compared to other spokes on the wheel. That is not the case with these brakes, and now I will try to explain that. Okay, here we have our wheel and our hub. Let's imagine this being a disc brake. This brake is firmly attached to the hub, it cannot turn. I have a video on disc brake mounting methods, about braking disc mounting methods, not the caliper itself, and which are better and worse for what reason. I will try to make it pop up if I don't forget when I'm editing this. So we have our disc brake that is attached to the hub, and we have our rim, our wheel, and let's draw our fork. Okay, and we have spokes. For this explanation I will use trailing and leading spokes because I think it's important to understand. So let's see. We have one. I'll draw just a few spokes. So these are our trailing spokes, and if this were the rear wheel and we were pedaling, they would be gaining some tension as we are applying the pedaling torque. There are also spokes coming from both sides of the hub's flanges, but here I'm drawing just one side, but the same thing happens with the other side. I have made a video experimenting whether the left-hand side spokes on a rear wheel also take the pedaling torque, concluding that they do in modern hubs that are quite rigid, in spite of that not having been the case before with steel hubs, like a lot like this one, in fact. But that is another topic for a separate video. Okay, so we drew our trailing spokes, and now let's draw our leading spokes. So we have one leading spoke here, we have another one here, we have another one here, and one here. Okay, so the wheel is trying to spin, and it's spinning in this direction, and we're trying to stop it from spinning. Again, we have our momentum of our weight and bicycle's weight trying to go forward, and we have the ground again exerting the same amount of force as is the force of our braking. So it will not be the same amount of force as our forward momentum, because then we will stop in place. So that happens when we are finally stopped, but when we start braking, it's a bit smaller than the forward going momentum, but it is the same as the momentum of the braking force, braking torque. And here we have the disc being held on by the brake caliper on the fork, effectively trying to prevent the hub from turning. So now we are not acting on the rim, but we are effectively trying to stop our hub from turning. Okay, so the hub is stopped and the ground is trying to move the wheel around. So what happens with the spokes, and how does that force of the rim being tried to still be pushed around by the earth translate to our hub, and vice versa? How does stopping the hub get transferred to stopping the rim from turning, the whole wheel from turning? Well, it goes through the spokes, of course, and what happens is that in this picture all the trailing spokes will lose some tension. Why? Because as we are trying to turn this rim around, we are effectively trying to turn the spoke from going like this to a bit more straight way, so at less of an angle, which is shorter. If we drew our triangle and try to calculate that, we would end up with this being longer than this, so these spokes will lose a bit of tension, while the leading spokes, when we are braking, will gain some tension for the same reason. So I will try to show it here on the wheel. As we are moving forward, this is the left side of the wheel, and these are the trailing spokes, and these are the leading spokes. So as we are holding the hub in place, stopping it by holding on to the disc brake, and the whole rim tries to move, what happens is that these spokes get pushed. They are trying to be elongated even further. It takes longer. We can show that using a simple method. Here, this spoke, you see where it ends now, and as I turn it to go further aside, the distance is further and further. I can make that extreme by having it all the way around. Then we have it shorter by this distance compared to having it here. And as it comes at an angle, the difference gradually increases the needed length, but it still needs a more length, so the leading spokes will get elongated as we brake. They will get more tension, and the trailing spokes will lose some tension. And so the entire force of our braking is distributed equally among both the left and right hand side spokes, even though the ones where the disc brake is, where the braking disc is, will take a bit more torque, because the transfer is not perfect. The hub is not 100% rigid, even the modern hubs, but they are a lot better than the old hubs that didn't transfer any torque to the opposite side spokes. I won't discuss that now in detail, but the principle is that the whole load gets equally spread around all the spokes by having half of them get a bit more tension and half of them lose a bit of tension. But that is a lot less stressful than having all the braking force be distributed unequally among fewer spokes. And that is why any concerns about overloading spokes when you're having disc brakes is a pretty moot point. A lot more stress happens when you are just pedaling and putting your weight. So you still need good strong wheels, even for disc brakes, of course, but not because you are using the brakes, but for other reasons. That is a common misconception that I hear and see, and I wanted to discuss it here. Now, the problem with disc brakes is that they put a lot more force on the bicycle's frame, on the fork, because all the stopping happens here, and this is a very long lever from the rest of the bicycle's frame and head tube, compared to having a rim brake mounted up here, so it has a very short lever compared to this one. So for disc brakes you need bicycle forks to be a lot stiffer, a lot stronger, and hence a lot heavier, and they do take more load, but not the spokes. Okay, so I think I've covered everything that I plan to cover in this video. I hope this was explained properly and that it helped you understand. And now I will talk a bit about wheel designs and why I've already explained why cross-lacing pattern is better at the start of the video practically. And now I will explain why it's a good idea to have more spokes and why it is a bad idea to have fewer spokes, and why paired spoke designs are also a bad idea. Here I will start with that. I will try to make that a picture of a wheel with the paired spoke design pop up. For some reason, some engineers thought that was a brilliant idea. Okay, so I've already explained why a bicycle wheel's strength is limited by the total total tension of all the spokes in a wheel. The higher the tension, the stronger the wheel, because whichever spoke gets unloaded, once it gets its tension to zero, the wheel will buckle. So it's important to have the total tension as high as the rim permits, with some margin of error like 20 to 30%, especially if you're using rim brakes. But it's important to have the total tension as high as possible, because there's always some other spoke being slackened, losing some of their tension when you're loading the rim, so you never know which one it will be, so the total tension should be as high as possible. And now, when we consider the wheel design, I'll first discuss the paired spokes. So with paired spokes design, you have two spokes coming from left and right side, ending at the same space on the rim, and that results in a situation like this. So instead of having the wheel, so let's try to draw it here with a very few spokes to make it clearer to understand. So instead of, here it is. Now when we use that kind of design, instead of having another spoke in between each of these be added, we would have it moved and placed at the same spot as the one here. So instead of having it like this, they practically move each of these to the nearest one and have them all in pairs. And what that does is that it creates a relatively long section of the rim without any spokes attached, while having double the tension in one single spot. So it is bound to make the rim deformed and have it looking a bit like this. They are making the rim effectively be a lot less round than it would have been for the same stiffness and strength of the rim had they not paired spokes but used the regularly spread spokes around the whole rim. So this is why that is a bad idea. So they will have the spokes ending up here and the rim being practically less round. This is exaggerated greatly, but the result is that you need a lot stronger rim for the same total spoke tension than you would have needed had you used a more, how do I say, less exotic spoke pattern and design pattern. So this is why I think the paired spokes are a very bad design. You need needlessly more weight to get more strength on the rim, and you gain nothing in terms of durability or even aerodynamics or anything. I think it's a complete nonsense. The similar thing goes for having wheels with too few spokes. Now it's modern to have, especially on road bicycles, to have a front wheel with just, I don't know, 24 spokes or something like that, or even fewer, maybe 16. So what happens? Well, say we want a given strength of the total wheel, a given total spoke tension. And let's say that we make a wheel with 36 spokes like this, and have each spoke, of course, for the rear wheel, the right hand side spokes, they come at a bit of a sharper angle, so they need more tension compared to the left hand side spokes in order to keep the rim in the center, to be in plane with the frame. That's a topic for a separate video. Here we'll assume that it's all symmetric, to make it simpler to explain. So let's say we have 36 spokes, and each of them has 80 kilogram force tension. Now, to get the same amount of total tension with, say, half of this number of spokes, let's use that for example, let's say 18 spokes. Okay. For that, we would need each spoke to have double the tension in order to get the same total tension of the wheel, which results in practically the same total wheel strength. If we go to a realistic number of 16, then we will need even more. I would have to calculate this. I cannot do it without using a calculator, but we would have to go roughly to about 880 kilogram force, perhaps, for each spoke. And the basic principle is that if we have more spokes, several spokes can share the same load more equally than is the case if we have fewer spokes. Also, in order to get the same strength of the wheel, we would need to use a lot higher tension that puts a lot more stress on the rim, and also creates a problem similar to what I've explained when I was discussing the paired spoke design. So those are the downsides. So you need practically a heavier rim to be more rigid, to be stronger, and you put a lot of force on the place where the nipples are pulled against the rim. So the rim interface to the nipple needs to be very strong, and there's a lot more stress on the threads of the nipples and on each particular spoke. Okay, the spoke itself is not a problem, but the rest of the contacts are weak points. So that is why I think it's not a very good idea to have a wheel with very few spokes. Another problem, especially with front wheels, is what happens if a spoke breaks. Even if you build the wheel properly and have a high quality wheel, you can always have some sort of accident, either something being hit against the spoke, or simply a manufacturing problem with one particular spoke and have it break. When you have very few spokes, here with our 16 spoked wheel, if one of the spokes breaks, we will lose a relatively high total percentage and absolute value of the tension. And the rim, even if it is very stiff, will move drastically to a side. It might move so much that it hits against the bicycle's fork and creates braking force by the tire rubbing against the fork, even blocking the wheel. And if you are descending fast or riding fast in traffic, that can be a problem. While on the other hand, with 36 spokes, if any of the spokes breaks, it's just a small percentage of total tension, and there is not so much instability. The balance is not lost nearly as much. So I've had experience of 36 spoked rear wheel having a spoke brake and the rim not even having started to rub against the rim brakes that were pretty close. So you could see when you looked at it that yes, it needs truing, but it was not something that made me have to stop immediately and fix it, but I could get home and do it when I'm happy to do it. So that is another reason why I think that having more spokes is better. So it creates a safer ride and it creates more durable, more long-lasting wheels. And any weight gains by having fewer spokes are negated by having to have a bit heavier rim. So it's not much of a trade-off. Aerodynamic benefits are a fact. If you have fewer spokes, especially if they are aero, and you ride really fast, so that that drag becomes an important factor in your total speed, and the total speed is very important for you if you're racing or competing, then yes, fewer spokes have their advantages, but for any kind of recreational riding, I think they are more of a liability in both terms of function, durability and security than they are a benefit. For example, I would rather go fast downhill on a 36 spoked wheels without a helmet and properly built bicycle generally than I would with a wheel front that is with 16 spokes only and with a helmet. That is how much I consider the few spoked wheels to be insecure. That is my opinion based on my experience. So that is for why I think that the more the merrier when it comes to spokes, especially for the recreational riding. And now I will only have one more thing to explain, if it hasn't become clear until now already when I was drawing those cross-laced wheels, and that is that spokes always come in pairs of 4. Maybe that's a wrong term to use, pair of 4, but you get the idea. So let's use this wheel as an example. Let's start from the valve. Here is the valve. We have one spoke. This is the leading spoke. And if we start from the valve, we have one spoke coming from the left-hand side of the hub, and the other adjacent one is coming from the opposite side. It is also, sorry, these are trailing spokes, my mistake. So we have 2 trailing spokes. Then we move on. We have one leading spoke coming from the left, and then we have one leading spoke coming from the right. And then it all repeats around the whole wheel. So the total number of spokes is always number 4 multiplied by a certain value, the whole numbers. So you have 2 spokes that are trailing, 2 spokes that are leading, always being laced alternately from left to right, left, right, left, right. And that's how it goes, and then goes trailing, leading, and so on. And you can see that there are 2 spokes that are like parallel. When you're lacing a wheel, this repeats every 4 spokes. So we have 2 parallel, 1, 2, 3, 4 parallel, 1, 2, 3, 4 parallel, 1, 2, 3, 4 parallel. So that also repeats around the whole rim. And we're lacing, if you do as I've shown in my video about lacing wheels and building wheels, you will have this aligned with one of these aligned with the valve, so that you have room to put your pump inside. And it would be a bad idea to have a valve here, because these spokes are going at an angle and you will have a very small amount of room to place your pump onto the valve and remove it afterwards. So that is another thing to pay attention to, and that is generally how this structure works around the whole rim. We always have these like paired spokes from left to right, so each is pulling to each side, keeping the rim in place by evening the tension. And the same thing happens with pulling and trailing spokes, again in the opposite direction, the force being used, and that happens around the whole rim, and that is what makes wheels to be strong, durable, long-lasting, and true and going well. So I hope I've made this video, I hope this video has helped you. I hope I've explained everything properly. I can recommend the book. I will try to make it pop up someplace here, written by Jobst Brandt. It's called The Bicycle Wheel, where he explains most of these things. And my only objection to that book is, because it's decades old now, the hubs from the time when the author was writing a book, they are deceased now, unfortunately. But at that time, hubs were made of steel, and they were not very rigid. They looked a bit like this, while modern hubs are a lot thicker and a lot more rigid. So the force from pedaling and from these brakes does get transferred to the opposite side of the hub, unlike he's explained in that book, because at the time the hubs were a bit less rigid, so they would twist and not place the load to the opposite side, not transfer it. So that's my only complaint, but everything else that I've talked about here is explained with all the formulas and how it was measured, and I would say it's a lot better than my Tarzan English, but also for me, I needed to visualize it and to try it in practice and to measure things to have it all sit in place, and that is what I've tried to do in this video. If you enjoyed this video, I might even make another one like this. That's it. Thank you very much for watching, and cheers. If you like this video, you can click on subscribe and choose this bell option, select all, so you get notified whenever I upload a new video.